In a world driven by noise, the man who first glimpsed antimatter barely spoke at all. Paul Dirac's silence was legendary, and his equations forced the universe to reveal hidden symmetries no words could touch. Born in 1902 in Bristol, England, under a father's iron rules, he let mathematics speak instead. He helped found quantum mechanics in the 1920s, and he wrote the Dirac equation that united quantum mechanics and special relativity. He predicted antimatter before experiment confirmed it. What happened in that quiet childhood that gave rise to physics' most disciplined mind? Bristol. At the turn of the 20th century was a city of brick terraces and narrow lanes. Paul Dirac was born there on August 8, 1902. His home in Bishopston sat beneath the discipline of his father, Charles, a Swiss-born teacher of French who brought the classroom into the family's everyday life. Conversation in the Dirac household was not casual. Charles required his sons to speak only French to him at home. If Paul could not find the right words, silence was the only option. Even minor mistakes brought correction, sometimes punishment. Meals could be eaten alone as a consequence, and conversations were often cut short. For Paul, words became risky, and silence often felt safer than speech. Family and friends later described the house as a place where sentences were rationed and mistakes carried a cost. Affection was rarely shown, and approval was measured in discipline. The air inside the house grew heavy with unspoken thought, and Paul learned to keep his own company. Within this environment, the habit of saying little took root. He grew up relying on observation and precision, learning that the wrong word could close a door. The quiet was not emptiness, but a careful shield, shaping a mind that would later trust symbols and equations more than conversation. In the quiet corners of Bishopston, Paul Dirac began to build a world where mathematics would become his true language. In 1923, Paul Dirac arrived at St. John's College, Cambridge, carrying a scholarship and a reputation for quiet diligence. The mathematics department was a world of chalk dust and hushed corridors where the boundaries of physics were being redrawn. Dirac's early work unfolded in silence, but the content of his papers spoke volumes. In 1925, while still a research student, he received a draft of Werner Heisenberg's new quantum theory. Dirac responded not with conversation, but with mathematics, developing his own approach to the puzzle of atomic behavior. His formulation, known as transformation theory, provided a powerful language that connected the scattered ideas of quantum mechanics into a single, coherent framework. By 1926, his papers were circulating among the leading theorists of Europe. He traveled to Copenhagen and Göttingen, joining the intense discussions that defined the new science, yet often said little in crowded seminar rooms. At the Fifth Solvay Conference in Brussels in 1927, Dirac took his seat among the giants, Bohr, Einstein, Heisenberg, and Schrödinger, his presence acknowledged by the quiet gravity of his equations. Within just a few years, his name had become a fixture in the letters and notebooks of the era's most influential physicists. By 1928, Dirac was recognized not as a visitor, but as a peer, a founder of quantum mechanics whose spare, precise mathematics was now essential to the field. In 1928, Paul Dirac published an equation that changed how physicists understood matter. Unlike any wave equation before, it wove together quantum mechanics and Einstein's special relativity. At its heart was a new mathematical object, a four-component spinor that described the electron not only as a point, but as a particle with intrinsic spin. The equation did not add spin by assumption. It produced spin as a consequence, matching the electron's magnetic properties and the fine details of hydrogen's spectrum. Yet, the mathematics went further. Hidden in its structure were solutions for particles identical to the electron, but with positive charge. In 1932, Carl Anderson, working with a cloud chamber at Caltech, recorded tracks from a particle with the electron's mass and opposite charge, the positron. Dirac's mathematics had predicted antimatter before anyone had seen it. In this equation, reality followed where mathematics led. Mathematical beauty, for Dirac, was not a luxury but a necessity. He once wrote that it is more important to have beauty in one's equations than to have them fit experiment. This conviction shaped every choice he made in physics. The Dirac equation, with its symmetry and elegance, was trusted not because evidence demanded it, but because its form felt inevitable. When his mathematics pointed to the existence of antimatter, a result that seemed almost fantastical, he accepted it, guided by the harmony of the equations themselves. Philosophical debates held little interest for him. He rarely joined in the arguments that filled seminar rooms, preferring the certainty of symbols over words. For Dirac, the path to truth was narrow and silent, lit only by the clarity of mathematical beauty. Recognition came quietly, as it often did for Dirac. In 1933, he was awarded the Nobel Prize in Physics, sharing the honor with Erwin Schrödinger for their discoveries in atomic theory. The citation named not only the new mathematics, but the transformation of how nature was understood. Among his peers, respect ran deep. Albert Einstein regarded Dirac's work as bold, even unsettling, but never trivial. Niels Bohr counted him among the select few who had built the foundations of quantum mechanics. Schrödinger, reflecting on the Dirac equation, wrote that it shines like a ray of light through the darkness of quantum theory. For Dirac, the applause was brief. He returned to his desk, letting the equations speak for themselves. In a world shaped by equations, Dirac's insistence on mathematical beauty still guides particle physics today. Quiet minds can shift reality, one silent calculation at a time.